All right, in this mini lecture, we're going to do a couple of things. We're going to kind of recap really quick simple harmonic motion and the equations of motion. And then we're going to use that information to learn how to solve problems of objects oscillating in that periodic fashion. We're actually going to look specifically at things on a spring, and we're going to use an ideal spring as our introduction, but the idea is that it provides a restoring force to get that object to move in simple harmonic motion. And then we'll do a quick practice problem to see how we utilize that information. So just to recap, again, that simple harmonic motion is this idea of periodic motion. And to review it really well, go to that mini lecture on the introduction to simple harmonic motion. But I do want to remind us that there are a few key features of that motion. We talk about an amplitude of the motion. So that's really how much displaced the object is from its sort of equilibrium position or its kind of natural position. And when we use our example today of a spring, it'll be that equilibrium position. We talk about the behavior itself, the timing of the motion. And so we introduce the idea of frequency, how many cycles the object makes in a certain amount of time, and then of course its inverse, the period, which represented how long it took for the object to make that cycle. And as a reminder, this behavior looked like a cosine function. So if we looked at the position as a function of time, we saw that it represented a cosine function. And so we had its amplitude, how high that wave looks in our position time graph. And then omega was our angular frequency, related, of course, to our actual frequency, where omega is equal to 2 pi times that frequency. Phi, again, was that kind of phase shift. Are we starting sort of in that equilibrium position, or are we shifting it by time? We're not going to use that a whole lot, but that is part of that relationship. All right, so let's think about this motion. Let's talk about an object on a spring. So we used this example before. If I have a spring hanging from a ceiling and I place a mass M on it, we know that that spring stretches to an equilibrium position where this mass is being pulled down by gravity, being held up by that spring. So what influences how much that spring is stretched? So we think back to our discussion of Hooke's law. Go ahead and check out that video to kind of remind yourself about this idea of a restoring force and Hooke's law. And we would remind ourselves that one thing that makes a difference is the spring constant. So how stiff that spring is. So if we think about a really stiff spring and I try to displace it and let this mass kind of bob up and down, what kind of effect would that have on the timing of it bobbing up and down? Or if I had a real loose spring, we're going to get a real big stretch, and if I had sent it bobbing up and down. We start to recognize that the stiffness of that spring does have an influence over the timing of our motion. So if I increase the stiffness of the spring, we want to think about, does that increase how long it takes for it to make a cycle? Or does it decrease how long it takes for it to make a cycle? Do I get faster oscillations if I increase K? Or do I get slower oscillations if I increase K? Well, it turns out we get faster oscillations. So if I increase the spring constant, the tightness of the spring, I increase the frequency. I get kind of faster oscillations. Think of a spring on a bobblehead, right? Pretty stiff spring. It kind of bobbles really quickly versus a spring that might be a nice child's toy that we want to go nice and loose and flowy. If I increase the frequency, of course, I decrease the period, how long it takes to do one cycle. If it's going really quickly, that time is shortened. So the spring constant itself matters. Well, what else might matter? One of the things we talked about in the previous video was that where this object oscillates depends on the equilibrium position. Remember, if I put a larger mass on the same spring, that larger mass is going to stretch that spring a little bit longer. If it stretches that spring a little bit longer, the restoring force, the force the spring exerts to help make it go up and down to counter that gravity, is going to be affected. Remember, the force by that spring is related to how much that stiffness of the spring is. We've already talked about that, but also how much it's stretched. And how much it's stretched is related to what? To the equilibrium position. It's related to what mass I put on it. So it turns out the mass itself also has an influence over the period of the motion. If I increase the mass, I get a longer stretch in that spring. You might predict that I increase that period. So it's going to take it longer to go up and down if it's in that long stretch state. And of course, that means I'm going to decrease my frequency. So it turns out the period and the frequency of a simple harmonic oscillator with a spring are related to both mass matters. Let's just do that. Are related to both the mass and the spring constant, and we're going to use that. The period of a simple harmonic oscillator on a spring is equal to 2 pi times the square root of the mass over the spring constant. And your book, any book that you're using, if it's a calculus-based book especially, is going to go through the derivation of that, looking at the equation for motion and the restoring force, how the restoring force dictates that motion, and it'll get to this value. But we're just going to use that and use that conceptual idea that, yeah, if I have a stiffer spring, it's going to take longer for that to make a cycle. And if I stretch that spring more, it's going to influence that timing of that cycle as well. So, of course, if this is the period of our motion, the frequency, which is equal to 1 over the period, we've talked about that in the previous lecture, can be written as 2 pi times k over m. And that, again, does certainly show consistency with that conceptual description that we talked about. So these are two really valuable tidbits of information as we look at simple harmonic motion of an oscillating object, and the example we're going to be using and kind of diving into is with springs. We will see similar relationships when we look at pendulums, and so keep that in mind, and then of course look for that mini lecture in another video. All right, so two good pieces of information. I'm just going to transfer these over here so that so for a spring in oscillation is 2 pi, the square root of m, over our spring constant. And the frequency, 1 over 2 pi, k over m. All right, let's kind of get rid of this a little bit. I'm just going to erase this and leave that equation up there because we did show in the previous lecture that maximum velocity could be determined using our derivative of our position equation, just as all derivatives of the position equation give us our velocity. And we found that maximum velocity, if we take that derivative, the velocity maximum of an oscillating object, remember, was 2 pi times the frequency times the amplitude. Okay, so I've talked about the frequency and what it's influenced by. But what about the amplitude? What influences the amplitude of the motion? Well, the amplitude of the motion is simply influenced by how much that object has been displaced from its rest state. So when we have a vertical spring, right, that rest state is the equilibrium point. How far beyond that equilibrium point the object has been displaced. And so the amplitude is controlled by that displacement itself. Notice, however, that the period and the frequency don't have any dependence on the amplitude. And that's really important to understand. The amplitude does not influence how quickly the object is oscillating from a period frequency perspective. But if I stretch my spring a lot further from its equilibrium, and it has to do the same cycle in the same amount of time because it's dependent on these two variables, we know it has to be moving faster. So that's where this relationship kind of sheds light on the behavior that we see. The amplitude gives us some indication about how linearly fast it's moving. If we had a little, a speedometer on it, how fast it would be moving. So it's really important to keep in mind when we think about simple harmonic motion that we want to think about both timing in terms of the wave pattern, how many cycles we make or how long it takes to make a cycle, and speed and timing as we think about how fast the object is moving. So keeping these equations in mind will help us solve some problems with springs and oscillations. Things like springs in your car or the toys that we've been talking about, bobbleheads, those sorts of ideas. All right, let's do a quick example and use this detail to solve a problem. I'm going to go ahead and erase this relationship and just kind of move it down here so that we remember what it is. Amplitude, I think I still have room. And then I'm going to actually move this one too. We will utilize this. I'm going to take out the phase. I'm just going to remind us that omega is related to that frequency. So our angular frequency is just 2 pi times our frequency. All right, so let's look at a problem and how we use this information to solve simple harmonic motion of a block on a spring. So we'll start very simply with just a block on a spring. Let's say we have a 200-gram block. It's attached to a spring. And that spring has a spring constant of 5 newtons per meter. All right. So let's say it's on a frictionless horizontal surface. Okay. All right, frictionless horizontal surface, and I pull that system to 5 centimeters. So I pull that mass 5 centimeters from its rest state. Here's what we want to determine. I gotta get a better blue marker. We want to determine first, what is the frequency? What is the period? What's its maximum velocity? How fast did we get this moving? And then where, relative to its rest position, is the mass at time equal, what did I use? 1.2 seconds. All right, so those 4 questions. Okay, so this is a mass on a spring. Let's just draw what this looks like. Here we have a mass. There's a spring and maybe attached to a wall. It's on a horizontal surface that's frictionless. If this is its natural state, I'm going to stretch that to the 5 centimeter mark. Let go of it. That restoring force pulls it back. We have some velocity as we go through center, through that equilibrium position, thus compressing that spring, and we are put into simple harmonic motion. Okay, the frequency. Well, we've learned that the frequency is equal to 1 over 2 pi times the square root of the k over m. I always have to look because I get those 2 backwards. It's fine. Let's not use our brain cells to memorize that. Let's just think about the relationship. I could deduce it. If I stiffen it, will I get faster oscillations? If I get faster oscillations, yes, that k should go on top. All right, now we can just calculate that. So we have 1 over 2 pi times the square root of k, which is 5, over the mass, and we need to make sure if we're in newtons that we're doing standard units of kilograms. So this is 0.2, and I get a frequency of, I did not write down the answer, so let's do it. So we have 1 divided by 2 pi times the square root of 5 divided by 0.2. And we get a frequency of 0.795 hertz. All right, so that's number 1. 2, the period. What's the period? Well, I could solve the period 2 ways. I could solve the period as 2 pi times the square root of m over k. Or we want to remember that the period is also 1 over the frequency. So let's just do both. Practice using our new equation. The mass, of course, is 0.2 over 5. And again, we use my trusty calculator. We have 2 times pi. And there's an alarm going off. I'm going to keep going. I'm just going to turn it off. Sorry. We're going to keep going on this video because we're on a roll. Okay. Back to business. 2 times pi times the square root of 0.2 and divided by 5. And we have a period of 1.26 seconds. And of course, if we do 1 over 0.795, let's hope that's also 1.26 seconds. So 1 divided by 0.795. And indeed it is. Thank goodness. It should be, right? We should definitely have the period the same both ways. So utilizing our new equation or reminding ourselves the relationship between period and frequency. What maximum velocity? When we looked at that in our last video when we introduced the idea of simple harmonic motion, we know that the maximum velocity is 2 pi times the frequency times the amplitude. So we have 2 pi, our frequency of 0.795. Our amplitude, I've displaced the system by 5 centimeters, so 0.05. So if we do that, we have 2 times pi times 0.795 times 0.05. We get a maximum velocity of 0.250 meters per second. Make sure I'm still on screen. Perfect. So again, utilizing that new equation that we learned in our last video, I guess, but utilizing in this situation. And then what about its position? Well, now we can write the equation of motion for our specific situation. So our equation of motion, x of t, is equal to the amplitude, which we know to be 0.05, times the cosine of 2 pi times the frequency, which is 0.795, times time. So our equation of motion is 0.05 times the cosine of, and I'm just going to do that out for us, so 2 times pi times 0.795. We get 4.9 or 5.0 t. And now if I want to determine the position at time equal 1.2, I can very slick plug in my 1.2 for time, and we find 0.05 times the cosine of 5 times 1.2 is 0.05 centimeters. So at 1.2 seconds, we are, sorry, that's meters, 0.05 meters. And what does that tell us? It tells us that we're at really near our maximum, and rounding tells us that it's at a maximum. Does that make sense? Well, if a period is 1.2 seconds, I'm making that full cycle in 1.2 seconds, okay? So if I'm starting at 5 centimeters and I make a full cycle, I should be back pretty close to that 5 centimeters if the time of my period is similar to the time of the motion I was looking for. Now, we, of course, can solve for time for any time, but wanted to use this to get that sense of, yeah, it should be consistent with what that period is. If I started at 5 and I make a full cycle, I should be really close to that 5 again. All right, so utilizing this idea of a simple harmonic motion, we use the example of a spring, thinking about that restoring force, thinking about what does that tell us about the motion itself. And again, the math is in your book, or you can look online, of course. But we really utilize these equations for oscillations in simple harmonic motion, in a spring, right? So they come from the idea of the restoring force and Newton's second law, utilizing just in practice that maximum velocity, and then again practicing with our equation in a calculation sense. All right, good job.